Okay, so welcome back. This is part 2 in our series where we show you how infrared remote controls work. And here I've got some LEDs that are controlled by this 24 button, very simple and inexpensive infrared remote control. And I encourage you to look at part 1 where we explain what is infrared, what does it mean, how does this all work. And in this video, we're going to look at how we can develop a very, very simple Arduino sketch that's only about 50 lines of code, something like that. And we're not going to use any external libraries. We're not going to import a 10,000 lines of code library that we don't need. We're going to develop our very own decoder that allows us to decode the signals coming from this remote control and determine which button was pressed. Now you can see here I've got the infrared sensor we talked about in the first video, and I've only got 3 connections to it. I've got plus 5 volts come from this regulated power supply, and I've got plus 5 volts here in the red and ground, and my third pin on this sensor is going out and it's going to the oscilloscope, and it's also going to an Arduino Nano. And we showed before that this is the burst of data you get when you press a button on this remote. And what we're going to show in this video is how to take all those ones and zeros and decode them in the Arduino to determine which button was pressed. And we're going to assign an integer number. Every time we press a button, it's going to decode that and assign an integer number to show us which button was pressed. Now, I encourage you, if you like any of these videos on this channel, please hit the like button and subscribe and hit the bell notifications. And most of all, please let others know that we're here so we get some more viewers. Really appreciate it. So as we showed in the previous video, our challenge will be, here is the burst of data we're going to get. And ones and zeros are signified by the width of the pulses. So we've got a narrow pulse and a wide pulse. So we're going to have to do something in the Arduino to discriminate between a narrow pulse and a wide pulse, which means we're going to have to measure the pulse widths. And what we're going to have is a normally high signal, and when a pulse is coming, it's going to go low to signify a pulse is coming. We're going to get this wide pulse that says, okay, after this, we're going to give you some data. And this is a 4.5 millisecond pulse. So our challenge with the Arduino is going to figure out some way to measure pulse widths. And if we can measure pulse widths, then we can say, okay, if it's a narrow pulse, it's a 0. If it's a wide pulse, it's a 1. So let's take a look at how we can do that, what things we can use in the Arduino to measure these pulse widths. So thankfully, the Arduino has a very wonderful function that can do exactly what we need, and it's called the pulse in function. So what does this do? Well, it does exactly what we need. It reads a pulse, either high or low, on a pin. For example, if the value is high, pulse in waits for the pin to go from low to high, then starts timing and waits for the pin to then go low and stops timing. It returns the length of the pulse in microseconds, or gives up and returns 0 if no complete pulse was received within the timeout value. So this is exactly what we need to measure our pulse durations. Now, importantly, it works on pulses that go from either 10 microseconds up to 3 minutes in length. So we have pulses that are like a minimum of maybe 500 microseconds. So this should be fine. This works on very fast pulses compared to what we're doing. So this should be the perfect solution. So what we're going to do is we're going to jump into the Arduino code and show how we're going to use this to measure our pulse durations and figure out the zeros and ones. So here is the Arduino sketch we're going to use to detect the infrared commands. And you can see up here I've got some initializing we're doing. The void setup is the standard serial begin 9600 baud. And pin mode, we're setting the pin mode to input. We're having the digital 2 pin as the input. And that's about it for all the initialization. Then we've got the loop. Now you can see the total code here is 75 lines. Much of it is comments. So really, we're talking 50 or 60 lines of code to do this, and you can see I have no libraries. I'm just using the standard Arduino sketch. So let's take a look at some of these initializing variables. I'm using the input pin as the digital 2 pin, And I'm setting an integer for the number of bits detected. Keep in mind we're going to have 32 bits. We're going to detect the duration of each of the bits, so we're just going to keep track of how many bits we've detected. And when we get to 32, we're done, we can finish. I've got some constant integers here, which is the total number of IR bits, and that's 32. We can change that for different formats of codes, but here we're going to deal with 32 bits. Our command byte is going to start at bit number 16 and go up 8 bits. So we've got start bit is bit 16, and the length of the command byte is going to be 8 bits. So we're just keeping track of those. We're going to use those to size our different arrays. We're keeping a Boolean if we detected the start bit, which is kind of the warning bit that says, hey, we've got some data coming. We can set this Boolean to true and then start collecting the data. So we've got that start detected Boolean. And then we've got our 2 arrays. The first array is a char array of all of the 32 bits. You can see it's the value is number of IR bits, which is 32. So this is the decoded zeros and ones for all 32 bits. So we're going to measure the duration of each of the pulses, convert those to zeros and ones, and put them in this vals array. The next one is just the subset, which is the 8 bits that specify the command or the actual that define which button was pressed. And this is going to be a 8-bit array of zeros and ones that define that. And then the last thing is an unsigned long, which is for each pulse, we're going to calculate the duration, the microsecond duration, using the pulse in method that we talked about. And that's going to hold that duration. We're going to then put that into the array. So those are our initializing variables, and we've got the void setup. Now the loop is just going to go through and wait for a pulse to come so we can figure out what's the duration and what is the pulse, what's the meaning of each pulse. So first thing we're going to do is we're going to wait for the input pin to go from low to high, and then start timing to determine pulse length using this pulse in command. And again, we're setting the microsecond duration as whatever the result of this pulse in using the input pin, which is our digital 2, and we're setting it as a value of high, which means we're waiting for a 0, and then the pulse is going to go high, and we're going to start counting when that pulse starts to go from 0 to 1. One thing to know about this pulse in is it has a timeout. In other words, it's going to wait for a 0 that goes to a high, and it's going to wait for a default of 1 second. So if it times out, if it doesn't get that within 1 second, it's going to return a value of 0 to this microsecond duration. So we're going to have to check to see if this duration is legitimate or if it's just a 0 and we just haven't received any data. So the pulse in is going to tell us the duration, or it's going to return a 0 if it's waited a second and never got a pulse. So now we've got the duration, and we have to check with this if statement what the duration was. This first if is going to discard the first or the warning pulse. It's going to say, hey, if I received a long pulse, we said it was about 4.5 milliseconds. If I receive that pulse, then I'm going to set the start detected Boolean to true and says, okay, we received the warning pulse, now start grabbing data. So if the result of the pulse in was a duration of greater than 3,000 microseconds or 3 milliseconds, and we haven't yet detected that warning pulse, so the start detected is false, then we say, okay, that was the warning pulse. So we can say we start detected is true, so we detected the warning pulse, and then we can return and start collecting the data. All right, so this if just discards the warning pulse. And we said the warning pulse is going to be at 4,500 milliseconds. So if it's greater than 3,000, we know it's the warning pulse. Let's say we've detected the warning pulse. Now we're going to check if we are in the collecting data stage. So if the number of bits detected, if the number of pulses detected is less than 32 in this case, we're waiting for 32 bits in this burst. If the bits detected is less than 32 and we've already detected the start pulse, start detected is true, then we can grab the burst, we can grab the bit and set it as either a 0 or 1 in our array. If the microsecond duration is greater than 0 and it's less than 800, we're going to say that it is a 0, and we're going to store that in the vals array. Each time we add a value to that array, we're going to increment the number of bits detected. Else, if it's greater than 800 and less than 2000, we know that it's a 1, so we're going to put in the vals array, instead we're going to put a 1 and increment the bits detected. So as we go through this, we're going to fill up the vals array with zeros and ones, and ultimately we'll have all 32 of these values filled in. If we've got all 32 filled in, the number of bits detected will equal 32, or the number of IR bits. And once we've got that, we can now, we've got all 32 bits as zeros and ones, we can now start parsing that array of values and figure out what the 8 bits, the 8 command bits are, so we know which button was pressed. So now let's take a look at some of the logic we're going to use to convert from the array of zeros and ones to an integer number, which is a lot easier to work with. Okay, so now we know that we're going to have an array of 8 zeros and ones that represent this 8 bits of command data that gives us an indication of which button was pressed on the remote. So it's going to be a 0 to 256 number that corresponds to the button on the remote. So now that we've got that array of zeros and ones, how are we going to convert that to something that's a little bit more usable, like an integer number? Instead of 0, 1, 0, 0, 0, 0, we'd like to have a number of 2, right? It's a little bit easier to use. So let's look into how we would do that, how we would convert that array of 8 zeros and ones into an actual integer number. Well, as I often do, I've jumped into Excel to give us a visual picture of how we might do that. So I've got here a simple spreadsheet, and this is a calculator, and it will calculate for a given set of zeros and ones. It will calculate the corresponding integer value. So in yellow here, I am representing the 8 bits of our command array, and we can fill in zeros or ones or whatever in these different cells, and it will calculate the corresponding integer value. So how does it do that? Well, as you probably or may know, with binary numbers, each bit represents a weight that is a multiple of 2. So for example, my least significant bit, or bit 0, if I have a 0 in that element, it represents a value of 0, which you see down here. However, if I put in a value of 1, it represents an integer value of 1. So if I add another bit, like I'm doing with this bit 1, I now have the ability to specify more numbers. So for example, this one I could only specify a value of 0 or 1, but with this I have 2 bits, and each can be a 0 or 1, so that gives me 4 possible numbers I can represent. So I can go 0 and 0, which gives me 0. I can go 1 and 0, which gives me a 1. I can go 0 and 1, which gives me a 2. Or I can go 1 and 1, which gives me a 3. So since these only have 2 states each, I can only get values that are from 0 to 1 plus 2 or 3. Now, if this is making your brain explode a little bit, keep in mind this is no different from what we do with decimal numbers, all right? Now, I've got a calculator that does exactly the same thing, but for decimal numbers. And the difference is each digit in the decimal or integer number is a multiple of 10, not a multiple of 2, like it is with the binary numbers. So let's say I wanted to represent a value of 255. Well, the least significant digit is the 5. I can put 5 in that digit. The next one is the 50, 255, so I can put a 5 because that's a multiple of 10. And now I've got 50 in 5, and this is a multiple of 100, and that's the 2. So I put in the 3 digits, I put in 5, 5, and 2, and that gives me a value of 255. So we're doing exactly the same thing as we do with binary numbers, only we're using multiples of 10 rather than multiples of 2. So if each bit has a value that is a weight of 2, depending on which position it is, we can figure out what the equivalent integer value is by recognizing that depending on the position, we figure out what the weight of that position is and just multiply the bit times the weight and then sum all of those up to get the integer value. And that's what we're doing here. So all we're doing is we are saying, okay, give me the bit from the array, multiply times its weight, which is a multiple of 2, and then add all of those numbers together to get the final integer value. So that's how we're going to approach the logic in our sketch to come up with an integer value. So here we are back in the code, and we're at the point where if we have detected all 32 bits, or bits detected equals number of IR bits, then we got 2 things we have to do. One is we have to extract the 8 bits that specify the command or which button was pressed. Then we have to convert those 8 bits into integers. And we've just talked about how we're going to do that. So basically what I'm doing is I am preparing the serial output where I'm going to specify what the command we received is. So I said serial.print and the command equals, and here we're going to figure it out. Keep in mind that the data we receive is going to have a least significant bit and a most significant bit. The question is, do we care? Do we really care what this command number is? Maybe all we care about is that it's a unique number for each button. So calculating the exactly correct number may not be high on our priority list. Just keep that in mind. You may care, you may not care, as long as you get a unique number for each button. This just describes how there are least significant and most significant bits, and if you care about that, you're going to have to think about that when you're generating a subset of command values. So what I've got here after the serial.print, I've got an integer. I'm going to use j as a counter. I'm initializing that to 0. And my final command value is going to be the integer number that's, after we convert the zeros and ones, is going to go into command value. So the first thing we have to do is we're going to make a char array that holds the subset of 8 bits. And what I've done here is I have made it so that you can either put them in directly based on the vals values, or you can do the reverse and put the high bit into the 0 bit. So what I've done here is I am going to start with the high bit in the vals array, which is the command start bit, which in our case is bit 16, plus the 8-bit length of the byte for the command, and I'm going to count down. I'm going to start out with that high bit and put that into command 0, and then I'm counting down. So I'm going from I equals that 24 minus 1, I'm counting down to the start bit, which is 16. You don't need to do that. I'm just showing you how you could do it if you cared about the least and most significant bit. So at the end of this, we have 8 bits in the command array, which represent the subset of the vals array. Now, once we've got that, all we need to do is convert that array into a command value. And we showed before how we just have to get a weight for each position in the command array and multiply those out. So what I'm doing is I'm going through for I equals 0 to I equals size of the command array, which is 8 bits in our case, and I'm going through each value. I'm multiplying the value, which starts out at 0. I'm multiplying it times 2, and I'm incrementing. Each time I get a 1, I need to multiply it times that weight. So if the command value is a 1, I'm incrementing that command value by 1, and the next time through I will double that. I will multiply it times 2. When I'm done here, my command value is going to represent the actual integer value specified by that command array. With that, we're all done. We've got an integer. The command value is the integer corresponding to the button that was pressed. And then all I'm doing is I'm doing a serial.println and printing out that command value. Okay, so now I have downloaded the sketch to my Arduino Nano, and I have hooked up the output of the sensor to the D2 pin on my Nano. And let's see what happens. I've got my serial monitor open. Let's see what happens as I press buttons on the remote control, see what I get. So I'm pressing the first button, I get a 0. The next one next to it, I get a 1. And you can see for each button, it gives me a unique number. Now again, does it matter what the number is or just the fact that it's unique? So whatever number you get, it may be fine, but at least we want to make sure it's unique. So that's about it for this one. Again, if you like any of these videos, please hit the like button and subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some more viewers. Appreciate it. Otherwise, take care. Have a really good day. Thanks.